Hello, ladies and gentlemen, welcome. Today we're going to discuss a Euclid contest question on functions. But before we start, just a general reminder that the Euclid contest is just around the corner in April, and given that it is March already, don't forget to sign up if you want to participate this year. So today we're going to take a look at a question number 7 on the Euclid contest. And as you guys may all know, the contest consists of 10 questions and the difficulty increases as you progress, with question 1 being the easiest and question 10 being the hardest. So a question number 7 is in the hard category. And another thing worth mentioning about this question is that it is one of those questions where the contest tests you on a relatively familiar concept or simple concept that you have already seen in the regular high school curriculum. But it tests you in a bit of an unfamiliar way, or in other words, the question is a lot more in depth than what you would normally get in a regular Ontario high school curriculum. So without further ado, let's take a look at this question on functions. This is question number 7a, right, on the 2020 contest. It asks, suppose that the function g satisfies g of x is equal to 2x minus 4 for all real numbers x, and that g inverse, or g negative 1, is the inverse function of g. Suppose that the function f satisfies g of f of g inverse of x is 2x squared plus 16x plus 26 for all real numbers x. What is the value of f of pi? Well, as you can see, right, there's nothing too outrageous about this question. It just involves a linear function, a quadratic function, and, then involves the concept of inverses. But before we start, we do want to go over the concept of inverses because this is a key concept that I think a lot of high school students that I've met, and their understandings of this concept are not 100% accurate, right? Like, they can tell me how to find an inverse, but they can't really, I guess, leverage this concept really well. So we're gonna look at this. So quick review. Inverse. Suppose that there's a function fx, right? And it maps from an x value to a y value. And suppose that this function has an inverse where f negative 1 exists, right? We know that not all functions have an inverse. So we suppose that there is such a function, f inverse. Then what f inverse does is that f inverse of f of x spits back out the original input, which is x, right? It undoes the f. Or in other words, there's a bit of an extension here. F inverse on the inside, so f of f inverse of x does the same thing. It just spits x back out, right? So this might be a little bit of mind-blowing for some of you. But okay, how exactly do you find such a function? Well, let's go over a really simple example. Suppose that we have a linear function mx plus b, and as you can see, currently the function has y isolated and x as an input, right, on the right side. So what we want to do is that we want to reorganize the equation such that x is isolated, right? So that x is a function of y. So what we do is that, okay, let's start peeling this, right? So do the undo the plus b first, so it becomes y minus b equals to mx. Then you undo the multiply by m, so that y minus b divided by m is x. So at the end, if you really want to swap the x and y, now you can do it. But the idea is that you want to reorganize and isolate the original input. Now, armed with this knowledge, let's take a look at this question. If I want to solve it, some people might say that, okay, I have g of f of g inverse. According to the properties of inverse, hey, isn't this just equal to fx? Therefore, f of pi is just, 2 pi squared plus 16 pi plus 26. Well, you can't be more wrong, right? So this is due to the, I guess, lack of the precise understanding of what the inverse does. Look. The inverse function only cancels out the original function, right? Only when they're right beside each other. So if you have f of g inverse, okay, in this case, yes, it is f of x. But if there is something between the g and g inverse, you cannot cancel out the effect of this function, right? So, okay, what is the right approach to this question? Actually, there are more than 2 methods, right? And what I'm about to show you is what I find the most intuitive. And if you want, you can dig in further and find out the other way, right? Okay, so what I did was that, look, let's look at what's given by the question. I have g of f of g inverse. That's a huge quadratic formula. And I have g of x. If you look at these two functions, right, there is actually something common. Like looking at the outermost function, you can see that in some ways, right, both functions are functions of g, right? They're all g of something, except that on the left side is a g of a really complicated expression, f of g inverse. On the right side is a very simple expression, just x. So they're really, if you read it in that way, they're both g of something. Also, right away, what I can find is that I can find the exact expression of g inverse because g is a linear function, right? And it's very easy to find the inverse, as we have seen in the previous section. You just reorganize such that you isolate the x, and then you can swap the x and y. So you'll see that the g inverse of x is simply x plus 4 divided by 2, right? So this is what we know so far. Immediately, I guess the immediately obvious facts from the question. Now, here's the thing. I know the exact expression of g. I know the exact expression of g inverse. I just don't know the exact expression of f. How do I find the exact expression of f? Well, the first thing that actually popped into my mind is that, okay, since both the equation on the left and the equation on the right, they are really just functions, just like functions of g, but with different inputs, right? One is f of g inverse, the other is just simple x. So let me reorganize or massage the function on the left, the g of f of g inverse, so that it looks more or less like the function on the right. So it looks more like the simple definition of gx, right? So what do? Well, I take the g of f of g inverse, right, which is a quadratic formula. Now, instead of adding 26, I add 30 and I subtract 4. Why do I do that? Look, on the right side, I have something subtract 4, right? And then I take the first 3 terms together. I factor out a 2, right? So in other words, this is really a function of g, because what g does is that it takes an input, multiply by 2, and subtract 4. So in this case, I have reorganized the function on the left to be, it's really a g function, but the input has been swapped from x to something of x squared plus 8x plus 15. This is a very important breakthrough for this question. Okay, so what we have at this point is g of f of g inverse of x is equal to g of x squared plus 8x plus 15. And we can conclude that the highlighted part, so this part on the inside, so f of g inverse of x must equal to x squared plus 8x plus 15. And some people might ask, why can you say that, right? Sometimes a function has same output but different inputs. Well, let me remind you, gx is a linear function. Therefore, if the outputs are the same, then the inputs must be the same. Okay, so at this point, we have f of g inverse of x is equal to x squared plus 8x plus 15. It is kind of a composite function and an explicit expression in terms of x. Remember, what we are interested in is finding f of pi, right? But what we have here is f of g inverse. This is a composite function. Okay, how can I find f of pi? Well, actually, you can see that if we can find an x value such that the g inverse of x is exactly the value of pi, then f of g inverse of x is essentially the same as f of pi. So then we ask this follow-up question, what is the value of x such that g inverse of x is equal to pi? Well, remember, we do have an explicit expression for g inverse of x. So we just make sure that this expression solves to pi. And if you do some algebra here, you'll see that x is equal to 2 pi minus 4. Okay, therefore, right, we know that when x is equal to 2 minus 4, right, f of g inverse of 2 pi minus 4, this is essentially the same as f of pi, right? So we go back to that expression x squared plus 8x plus 15. Everywhere we see x, let's replace it with 2 pi minus 4. And if you do some algebra, you will see, first of all, that's a perfect square expansion. Then you expand the second bracket, and then you just make sure you collect the like terms and cancel things out. The exact answer to this question is actually 4 pi squared minus 1.